Welcome to Gamma Classroom. Today I'm going to introduce the series video 1.4 Series and Parallel Circuits. 1.4-1 What are series and parallel circuits? Circuits consisting of just one battery and one load resistance are very simple to analyze, but they are not often found in practical applications. Usually, we find circuits where more than two components are connected together. There are two basic ways in which to connect more than two circuit components, series and parallel. First, an example of series circuit. Here we have three resistors labeled R1, R2, and R3, connected in a long chain from one terminal of the battery to the other. The defining characteristics of series circuit is that there is only one path for current to flow. In this circuit, the current flows in a clockwise direction. From point 1, the current from point 1 to point 2, and to point 3 to point 4, and back to the point 1. Now, let's look at the other type of circuit, a parallel configuration. Again, we have three resistors, R1, R2, and R3. But this time, they form from more than one continuous path for current to flow. There's one path from 1 to 2, and to 7 to 8, and back to 1 again. Then there is another from 1 to 2, and to 3 to 6, and back to 7 to 8, and back to number 1. And there's a third path from 1 to 2 to 3 to 4, and then through the resistor to 5, back to 6, back to 7, back to 8, and back to 1 again. Each individual path through R1, R2, and R3 is called a branch. This is the branch. This is another branch, and this is another branch. The defining characteristics of a parallel circuit is that all components are connected between the same set of electrically common point. Looking at this schematics, we see that point 1, 2, 3, and 4 are all electrically common, and so the point 5, 6, 7, and 8 are electrically common point too. So that all resistors as well as the battery are connected between the two sets point. So R1, is connected to this common point set, and those common point set. So R1 is connected to 2 and 7. R2 is connected to 3 and 6. R3 is connected to 4 and 5. Since 1, 2, 3, 4 are electrically common point, the voltage is the same, exactly same. If we ignore the resistance between the 2 point, this point, the resistance in the wires, because the resistance is very small. We can have circuits that are a combination of series and parallel. In this circuit, we have two loops for current to flow through. One is from point 1 to point 2 through the resistor R1, like this. And from 2 to 5 through resistor R2, like this. And from 5 to 6. And from 6 back to number 1. This is one loop. The current comes from here, go like this, and make a loop here. And another from 1 to 2 to 3. The same through the resistor R1, but like this. And from 3 to 4 through resistor R3, like this. And from 4 to 5 and back to 6. And from number 6 back to number 1 again. This is this loop. From here, go far away to here, go back to here, and go back to the battery. And this is another loop. They have two loops. One is this way. The another one is from here to here, through R3, go back to the battery. They have two loops. One is through R2, another one through R3. This is just a preview of things to go. Down the road, we will explore all those circuit configurations in details, one at a time. Let's go back to series circuit, or called series connection. The basic idea of series connection is that components are connected end to end in a line to form a single path for currents to flow. Like this is a resistor. And this end is connected to another point. And this end is connected to the R2, the first end. And the R2, the second end, this way, is connected to the R3 first end. The same thing, the R3 second end is connected to the R4, the first end. And the R4, the second end, is connected to another piece of components. Like this connection is one end by the another end connect together. We call this connection is series connection. It forms only one path for current to flow. So the current can flow this way. From here, go this side. from this point to this point through all the resistors. All the current come from this side, go this direction is the same. Both are the same. It's okay. Both are okay because the resistor low direction they both the same. From this side go to this side, the resistance the value equal to from this side go to this side exactly the same. So this is a series connection. The basic idea of a parallel connection, on the other hand, is that all components are connected across each other's leaders. In a purely parallel circuit, there are never more than two sets of electrically common points. No matter how many components are connected, there are many paths for current to flow, but only one voltage across all components. This is the parallel connection. This resistor, the first end, is connected to the R2 first end, and the connect to R3 first end, and also connect to R4 first end. You can connect many resistors. Doesn't matter how many. You can connect all as many as you want. But you see this, the second end is connected to the R2 second end and connect R3 second end or the R4 second end. So all the second end connect together and form those points are electrically common points. It means this point is the same, the voltage is the same, and this point, the voltage is the same too. All the points, the voltage, because we ignore the resistance between those wires. The wire is short and the resistor is very, very small. We can ignore all the resistance between the wires. So we can say this point voltage is exactly equal to this point voltage, and is exactly equal to this point voltage, the same and so on. Or if you connect many resistors, all the points are the same voltage level. And this point the same, this voltage is the same. This point with this point, and many all the connect the same point, the voltage level is the same. This connection we call the parallel connection because this resistor is parallel with this one, and so on, so on. Series and parallel resistor configurations have very different electrical properties. We all explore the properties of each configuration in the sections to come. 1.-2 Simple series circuits. Let's start with the series circuit consisting of 3 resistors and a single battery. This is the battery, only one single battery here, 9 volt. And they have 3 resistors in the circuit, one R1, R2, and R3. And R1 connected. This end is connected to the battery, and this end, the second end, is connected to the first end of R2, and the second end of R2 is connected to the first end of R3, and the second end of R3 is connected to the battery. So this connection is a series connection. The first principle to understand about series circuits is that the amount of current is the same through any components in the circuit. You must remember this principle if you want to do the electrical job in the future. This principle you must be remember and understand. The first principle is talking about the amount of current in this circuit is the same everywhere. It means is I1, I2, I3 all the same. I1 equal to I2 equal to I3. This is because there is only one path for current to flow in a series circuit, and because current flows through conductors like marbles in a tube, the rate of flow means marble speed at any point in the circuit or tube at any specific point in time must be equal. Since point 1 and point 2 are connected together with wire of negligible resistance, we can say point 1 is electrically common to point 2, and the point 3 is electrically common to point 4. Since we know we have 9 watts of electromotive force between point 1 and point 4 directly across the battery. And since point 2 is common to point 1 and point 3 common to point 4, so we must also have 9 watt between point 2 and point 3 directly across the resistor. So this voltage is 9 watt. Therefore, we can apply almost now I equal to E divided by R to the current through the resistor. Because we know the voltage E across the resistor and the resistance R of that resistor. All terms E, I, R applying to the same 2 points in the circuit. It's the number 2 and the number 3. To that same resistor. So we can use the Ohm's law formula with no reservation. So we can get the current I equal to 9 watt divided by 3 kilo ohm. We can get 3 milliamp. So in this circuit, the amount of current is 3 milliamp. However, in circuits containing more than one resistor, we must be careful in how we apply Ohm's law. In the 3 resistor example circuit below? We know that we have 9 volts between point 1 and point 4, which is the amount of electromotive force trying to push current through the series combination of R1, R2, and R3. However, we cannot take the value of 9 watt and divide it by 3K, 10K, or 5K ohm to try to find a current value, because we don't know how much voltage is across any one of those resistors individually. The figure of 9 watts is the total quantity for the whole circuit, whereas the figures of 3K, 10K, and 5 kilo ohm are individual quantities for individual resistors. If we were to plug a figure for total voltage into an almost null equation with a figure for individual resistance, the result would not relate accurately to any quantity in the real circuit. For R1, almost null will relate the amount of voltage across R1 with the current through R1, giving R1's resistance 3 kilo ohms. The IR1 equal to ER1 divided by 3 kilo ohms, and ER1 is equal to current IR1 times 3 kilo ohms. Just pay attention, the ER1 means is voltage drop across R1 only. But since we don't know the voltage across R1, only the total voltage supplied by the battery across the 3 resistors series combination, and we don't know the current through R1, we cannot do any calculations with either formula. The same goes for R2 and R3. We can apply the almost null equations if and only if all terms are representative of their respective quantities between the same 2 points in the circuit. So what can we do? We know the voltage of the source is 9 volts, applied across the series combination of R1, R2, and R3. And we know the resistance of each resistor. But since those quantities are not in the same context, we cannot use almost null to determine the circuit current. If only we know what the total resistance was for the circuit, then we could calculate total current with our figure for total voltage. This means I equal to E divided by R. This brings us to the second principle of series circuits. The total resistance of any series circuit is equal to the sum of the individual resistance. This should make intuitive sense. The more resistors in series that the current must be flow through, the more difficult it will be for the current to flow. In the example problem, we had a 3 kilo ohm, 10 kilo ohm, and 5 kilo ohm resistor in series, giving us a total resistance of 18 kilo ohm. According to the second principle, in a series circuit, the total resistance is equal to the sum of all the individual resistors. We know in our example problems, and there are 3 resistors. R1 is equal to 3 kilo ohm. R2 is equal to 10 kilo ohm. And R3 is equal to 5 kilo ohms. So the total resistance equal to 18 kilo ohm. In essence, we have calculated the equivalent resistance of R1, R2, and R3 combined. Knowing this, we could redraw the circuit with a single equivalent resistor, representing the series combination of R1, R2, and R3. We can redraw the series circuit like this. Still is one battery, 9 volt, but we change 3 resistors to only one resistor in the circuit. But this resistance is equal to R1 plus R2 plus R3 is equal to 18 kilo ohms. This resistor we call the equivalent resistors. Now we have all the necessary information to calculate circuit current. Because we have the voltage between 0.1 and 0.4, it means equal to 9 volts, and the resistance between 0.1 and 0.4 is equal to 18 kilo ohm. Let's do the calculation. So we can calculate the current according to the norms now. So I total is equal to E total divided by R total. We know the E total from the battery is equal to 9 volts, and the total resistance is 18 kilo ohms. So 9 volt divided by 18 kilo ohms, we can get is 500 micro A. Micro means 10 powers minus 6. Knowing that current is equal through all components of a series circuit, and we just determined the current through the battery, we can go back to our original circuit schematic and note the current through each component. Let's look back the original series circuit. There are 3 resistors, R1, R2, and R3. We already do the calculation. The total current in the battery is 500 microamp. And according to the first principle, in a circuit, in a series circuit, the current in every component is the same. So the current in R1, R2, and R3 is the same, equal to 500 microamp. Now we know the amount of current through each resistor. We can use ohms now to determine the voltage drop across each one, applying the ohms now in its proper context. The voltage drop ER1 means cross over the resistor R1 is equal to the current passed through the R1 called IR1 times the R1 value. We know the current passed through the resistor R1 is 500 microamp. So times the value of the resistor is 3 kilo ohm. So we can do the calculation. 500, it means it's 5 times 10 power 2. And the microamp, it means it's times 10 power minus 6. And the 3 kilo ohm is times 3 times 10 power 3. So we can move the 1.3 times 5 equal to 1.5 and times 10 power 2 minus 6 plus 3 plus 1. We can get the value is 1.5 watt. This for the resistors, the voltage drop across the resistors R1. We can do the same calculation for resistor R2. ER2 equal to IR2 times R2. And the current is the same. IR2 is 500 microamp times the resistor 10 kilo ohm. So we can get 5 watt. The same, we can do the calculation for the ER3 equal to IR3 times R3. So the current is still 500 microamp times 5 kilo ohm. We get the voltage drop is 2.5 watt. Let's look back to the series circuit schematics. After do the calculation, we already found all the information for each resistors. For resistor R1, we know the value is 3 kilo ohm and the current is 500 microamp and the voltage drop is 1.5 watt. And for the R2 resistor 2, we know the value is 10 kilo ohm and the current is 500 microamp and the voltage drop is 5 watt. And for the resistor R3, so we know the resistor value is 5 kilo ohm. Then we get the current is 500 microamp and the voltage drop is 2.5. And for the battery, we know the current is 500 microamp and the voltage rise or voltage drop is 9 watt. So from these schematics, we get all the information that we need. Notice the voltage drops across each resistor and how the sum of the voltage drops 1.5 plus 5 plus 2.5 is equal to the battery supply, the power supply voltage 9 watts. This is the third principle of series circuits, that the supply voltage is equal to the sum of the individual voltage drops. You have to remember this third principle. However, the method we just used to analyze this simple series circuit can be streamlined for better understanding by using a table to list all voltages, currents, and resistance in the circuit. It becomes very easy to see which of those quantities can be probably related in any almost null equation. This table is to illustrate the relationships between all the components in the circuit. We know in our series circuit, there are only 3 resistors in the circuit. So we put the R1, R2, R3 for the 3 resistors. If there are more than 3 resistors in the circuit, you can add the more currents and move the R total to the right side. So in this law, this is E, it means it's voltage drop. So in this cell, it will be the voltage drop across R1. And this cell is the voltage drop across R2, and so on. This is the current. In this cell, it means the current passes through R1. And in this cell, it means this current passes through R2, and so on. And in this row, in this cell, it means what is the resistor R1 value and what is R2 value, and so on. How to fill this table? Let's start from the original series circuit schematics. This is the schematics. We know the battery is 9 volt. So if you look at from point 1 and point 4, look at this side from the right side, you can see all the resistors connect together. And this 2 point we can call is for the R total. And E is means the voltage drop. For the R total voltage drop, it means from point 1 to point 4. And since the voltage drop from point 1 to point 4 is 9 volt. So that means from point 1, the current passes through this way, and back to 4, the voltage drop is equal to 9 volt. So we can fill this cell with 9. That means for the total voltage drop is 9 volt. And also from these schematics, we can find the resistor R1 is 3 kilo ohm. So we can, because this in this law, the R, this cell means the value of the R1. So R1 here is told you is 3 kilo ohm. So we can put the 3K in this cell. It's 3K. The same, we can find R2 is 10 kilo ohm. So we can fill this cell with 10 kilo ohm. And the same R3, they have 3 kilo ohm. So we can fill this cell with 5 kilo ohm. So now, according to the original schematics, we can fill all the original data. 9 watt, 3 kilo ohm, 10 kilo ohm, and 5 kilo ohm. So those information we found from the original schematics. We couldn't find any others. So how to continue to fill this table? And let's take a look this table. For now, we already know all the individual resistors values. So 3K, 10K, 5K. So let's recall the principle for the series circuit. We know the second principle talk about the total resistance of any series circuit is equal to the sum of the individual resistors. So for now we know all the individual resistors. So we can get the total resistor here. So let's do the calculation. And for all this one, and do the calculation, R total should equal to sigma Ri equal to R1 plus R2 plus O until to Rn. In this circuit, we only have 3 resistors, so we can do the calculation and plus all the 3 resistors. It is 18K. We already get the total resistance in the circuit. How to continue to fill the table? Let's look at this current. You can find in this current, we already know the voltage drop. And we already know the total resistance. So according to the ohms law, so if we know any two quantities, we can calculate the third quantity. So we can apply, because you see we can see the original schematics. Since we already get the total resistance, we know this is only use one resist to replace the 3 resistors in the circuit, but the value is equal to the total of the 3 resistors. So now we can apply the Ohm's law to this circuit, because this point with this point is the common electrical common points, and this point with this point is the electrically common point. So now we can apply the Ohm's law on this current. So let's do the calculation. We know the current equal to E divided by R. We know the E, the voltage drop, is 9 watt. And we know the resistor, total resistor, is 18 kilo ohm. So after the calculate, we know the current is 500 microamp. So we can fill this cell with 500 microamp. So now, how to continue to fill all the other cells? We already get the current for the total resistors. So let's recall the principle, the first principle. The amount of current is the same through any component in the circuit. So in the circuit, we already know that current is 500 microamp. So should be the same, all the cells should be the same number with 500 microamp. So now we can fill the cell for this one is 500 microamp means the current passed through the R1 is 500 microamp. The same, we should fill the number 500 microamp for R2, and the same, we should fill the 500 microamp for R3. So for now, how to continue to fill the table? So let's take a look this current for R1. We already know two quantities, so we can apply the Ohm's law to find the third one. So we can apply the Ohm's law in this current. So we can do the calculation. So E, so this is voltage drop, equal to I times R1. I is 500 microamp pass through the R1 times R1 is 3K, 3 times 10 power 3. So we can get the voltage drop is 1.5 watt. So we can fill the 1.5 watt to this current. So we can do the same calculation or apply the Ohm's law in the R2. So take a look, this current, the same. We apply the Ohm's law. So we can do the calculation for the R2 because the resistor is 10 kilo ohm. So we can get 5 watt in this cell. We can fill the 5 watt in this cell. So we can do the same for R3. So we can look at this current and apply the Ohm's law and do the calculation for the R3. Since the R3 resistor value is 5 kilo ohm, so we can get 2.5 watt in this cell. So we just fill this 2.5 in this cell. We already learned how to showing all the calculations, all the results. One is use the schematics. We did all the calculation and put all the information on each components. The another way, we use a table. Use a table to fill all the information, all the calculation. So both way are good for you to use in the future. And most time probably we did like this because you will see a lot of the schematics and you do the calculation on the joints. But this table is when you get a more complex or more calculations, you can use the Excel sheet and put the formula inside. You can get the result fast and the higher accuracy. So both are okay, but you have to fully understand what exactly they are talking about. For example, in this resistor, we have all the information. The value of the resistor 3 kilo ohm in the table is same showing 3 kilo ohm, and the current is 500 microamp. Here is 500 microamp, and the voltage drop is 1.5. This is 1.5, and the same with R2, R3. Only thing in the schematics join didn't showing the total resistors. Here they have total resistor in this circuit. So I hope you fully understand both and you can use those two wheels in the future. 1.4-3 Simple parallel circuits. Let's start with the parallel circuit consisting of 3 resistors and a single battery. This is the battery. This is R1 with 10 kilo ohm. This is R2, 2 kilo ohm. This is R3, 1 kilo ohm. We already know these points are electrically common points, and those points are electrically common points too. So all the resistor is between the two common points. This is the parallel circuit. It means those resistors connection with parallel connection. The first principle to understand about parallel circuits is that the voltage is equal across all components in the circuit. This is because there are only two sets of electrically common points in a parallel circuit, and the voltage measured between sets of common points must always be the same at any given time. Therefore, in the above circuit, the voltage across R1 is equal to the voltage across R2, which is equal to the voltage across R3, which is equal to the voltage across the battery. This equality of voltages can be represented in another table for our starting values. We can create a table similar with the series connection. In this law, it's showing the components in the circuit. In above the parallel circuit, there are only three resistors in the circuit. So we call R1, R2, R3. If more than three resistors in the circuit, for example, they have 5 resistors in the circuit, you can add the current R4, R5, and move the total to the right side. And in this law, this is the voltage drop in this cell means it's a voltage drop in the R1. This is in the R2, and so on. This current, this is talk about the current. The unit is amps. So in this cell, means what the number of the current pass through the R1, and this pass through R2, and so on. This in this law, means the R1, the resistor value. What is the value for R1? What is the value for R2, and so on. Let's check the parallel circuit. This is the parallel circuit. We can find all the original data from these schematics. We know this is voltage from the battery. The total voltage is 9 watt. So we can fill this number with 9. We can find this. This is the total. R total means for this resistor R total. And the voltage drop is between the total. And we know the resistor R1 is 10 kilo ohm. So we can find here 10 kilo ohm. And also we know the R2 is equal to 2 kilo ohm. So we can fill the 2K in this cell. The same, we can find R3 is equal to 1 kilo ohm. You can fill this cell. So now we get all the origin number and filled in the table. We can use the first principle for parallel circuit to fill this table. The first principle is talk about the voltage is equal across all components in the circuit. We know the components in the circuit is R1, R2, and R3. Since the battery voltage is 9 volt, so in the circuit, every component's voltage should be the same. So we can feel R1 voltage should be 9, and R2 should be the same, 9 volt, and R3 should be the same, 9 volt. So we can feel all the voltage drop in this now. Let's take a look at this current for R1. We know the voltage drop across R1 is 9 volt. And we already know the R1, the resistor value is 10 kilo ohm. Since in ohms now, if we know two quantities, then we can find the third quantity. So we can apply the Ohm law in this current. So we can do the calculation in this current. The current is equal to E divided by R. We know the E is 9 volt and the R is 10 kilo ohm. So we can get the number is 0.9 milliamp because this is 10 power minus 3. So we get the number 0.9 milli. The M means the milliamp. So in this current, we already found all the three quantities. Voltage drop, the current passed through the R1, and the value of the resistor. The same for the resistor R2. Let's take a look at this current. We know the voltage drop across the resistor R2 is 9 volt. We know the resistor value is 2 kilo ohm. So we can apply the ohms now for this current. So we can do the calculation. The current is equal to the E divided by R. The E is 9 volt. The R is 2 kilo ohm. So we get the current is 4.5 milliamp. We can fill this cell with 4.5 milliamp. The same for the resistor R3. In this current, we know voltage drop and what the resistor value. So we can apply the ohms law. And we can do the calculation. Then we can get the current is 9 milliamp. Now only two cells are allowed filled in the table. One is the total current. The another one is the total resistance. Total current, total resistance. How to get the total current and the total resistance? Let's take a look at the parallel circuit again. As the total current flow out from the positive terminal of the battery at the point 1, the current flow out from the positive terminal at the point 1 and go this way. and traverse through the circuit. Some of the flow splitters off at point 2 and go down through R1 to point 7, and some more splitters off at point 3 to go down through R2 to point 6, and the remainder goes down through R3 to the point 5. Like a river branching into several smaller streams, the combined flow rates of all streams must equal the flow rate of the whole river. The same thing is encountered where the currents through R1, R2, and R3 joined to flow back to the negative terminal of the battery. And toward point 8, the flow of currents from point 7 to point 8 must be equal the sum of the branch current, through R1, R2, and R3. So that means the current flow in this path, I total, should be equal the sum of R1 and R2 and R3. The same thing, the water goes back to the battery. The current should be equal to the sum R1 and R2 and R3. This is the second principle of parallel circuits. The total circuit current is equal to the sum of the individual branch currents. Using this principle, we can fill in the I total support on our table with the sum of IR1 and IR2 and IR3. Let's go back to the table. Since the total current in a parallel circuit is equal to the sum of all the branch current for all the branch current, and in the current, if resistance 1 is 0.0 milliamp and R2 is 4.5 milliamp and R3 is 9 milliamp. So we plus all the three atoms, we can get the total current. I total equal to IR1 plus IR2 plus IR3. So we can get the 14 milliamp. So we can fill the cell with 14.4 milliamp. So now, since we get the total current as 14.4 milliamp, and look at this current. In this current, we already get the voltage drop for 9 watt, and the total current is 14 milliamp. So we can get the certain quantity through Ohm's law. So we can apply the Ohm's law in this current and do the calculation. The total resistor is equal to the total voltage drop divided by the total current. We know the voltage drop is 9 watt, and the total current is 14.4 milliamp. So we get the total resistance is 625 ohm. So we can fill this cell with 625 ohms. Please note something very important here. The total circuit resistance is only 625 ohm, less than any one of the individual resistors. In the series circuit, where the total resistance was the sum of the individual resistance, the total was bound to be greater than any one of the resistors individually. Here in the parallel circuit, however, the opposite is true. We say that the individual resistors diminish rather than add to make the total. This principle completes our triad of rules for parallel circuits, just as series circuits were found to have three rules for voltage, current, and resistance. Mathematically, the relationship between total resistance and individual resistance in a parallel circuit looks like this. The same basic form of equation works for any number of resistors connected together in parallel. Just add as many reciprocal R terms on the denominators of the fraction as needed to accommodate all parallel resistors in the circuit. So for the formula, the total resistor is equal to 1 divided by all the total of reciprocal R1 plus reciprocal R2 plus blah blah plus R reciprocal Rn if there are n resistors in the circuit. For our examples, it's only 3 resistors in the circuit. So this number should be 3, R1, R2, and R3. In summary, a parallel circuit is defined as one where all components are connected between the same set of electrically common points. Another way of saying this is that all components are connected across each other's terminals. From this definition, 3 principles of parallel circuits follows. The first principle: the voltage is equal across all components in the circuit, like this. This is the R1, R2, R3. So the voltage is equal to all the components. The second principle: the total circuit current is equal to the sum of the individual branch currents. This is the total current. So this number is equal to the sum of those individual branch current, 14.4 4 is equal to 0.9 plus 4.5 plus 9. The third principle, resistance diminishes to equal a smaller total resistance in a parallel circuit is less than any of the individual resistance. If there are n resistors in a circuit, we can use this formula to get the total resistors. The resistors are total resistors equal to 1 divided by the sum of reciprocal R1 and reciprocal R2 and more, and the last one, the reciprocal Rn. So in our examples, there only have 3 resistors in the circuit. So we can use those data put in the formula. We can get the total resistors as 625 ohm. This is all that we should learn in this video today. So let's review the main point for this video. The number 1, in a series circuit, all components are connected end to end, forming a single path for current to flow. Number 2, in a parallel circuit, all components are connected across each other, forming exactly 2 sets of electrically common points. Number 3, components in a series circuit share the same current. That means I total equal to I1 equal to I2 equal to Rn. Number 4, total currents in a parallel circuit is equal to the sum of the individual branch currents. It means I total equal to I1 plus I2 plus more plus Im. Number 5, total resistance in a series circuit is equal to the sum of the individual resistance. R total is equal to R1 plus R2 plus more plus Rn. Number 6, total resistance in a parallel circuit is less than any of the individual resistance. So the R total is equal to 1 divided by the sum of reciprocal R1 plus reciprocal R2 plus reciprocal Rn. Number 7, total voltage in a series circuit is equal to the sum of the individual voltage drops. So E total equal E1 plus E2 plus more plus En. The number 8, components in a parallel circuit share the same voltage. It means E total equal to E1 equal to E2 equal to En. Since the series and the parallel circuits are the most important basis for the electrical theory, if you want to do the electrical job in the field, you must understand and remember all the series and parallel principles. Thank you for watching. See you next time.